This is the fourth and last part of this video lecture, not the fifth part, as I say sometimes in the upcoming parts. So this is already the fifth part of this rather long video lecture. In the previous parts, we saw that how to prove the main axioms of the integral of non-negative extended Borel functions, and well, homogeneity was proved directly using the definition of the integral as a supremum. Additivity was proved using the previous video lecture that non-negative functions can be approximated by simple functions, and combine that with the monotone convergence theorem. And sigma additivity, well, there's nothing to prove. Once we have monotone convergence theorem, sigma additivity going from monotone convergence theorem to sigma additivity or back is just a formality. Then we use this pattern or this very standard approach of once something holds for binary functions, then we can, by using linearity, we can just take combinations of binary functions. This will give us simple functions. And by using monotone convergence theorem and the fact that every non-negative extended Borel function can be approximated from below by a sequence of non-decreasing simple functions, so we can combine that and use the monotone convergence theorem to bootstrap the same property for non-negative functions. And we can go from non-negative functions to general functions by separating the positive and negative parts. So here we separate positive and negative parts. Here we just use monotone convergence theorem, and here we just take a linear combination. So we use linearity. And the very same pattern, since already last week we had proved this one, and we just apply the pattern to go from here to here, and we follow the exactly same pattern here to prove the form for change of variable. We started with binary, went to simple, then non-negative, and finally general functions. And now we can prove properties of the Lebesgue integral, but we think of the Lebesgue integral defined for general functions using the fact that it was defined for non-negative extended Borel functions last week using axioms, but now not relying on axioms anymore. We have proved the axioms, and we're going to use them to bootstrap those properties to the general Lebesgue integral. So let's start with monotonicity. That will be the simplest case. If a function is always above another function, extended Borel functions, and well, we can suppose that the positive part of f has a finite integral, because otherwise we can assume that the negative part of g has a finite integral, because if neither of these two hold, then the conclusion of the monotonicity property is trivial. There is nothing to prove. Yes, if the integral of f is infinite or undefined, or the integral of g is minus infinite or undefined, then there is nothing left to prove, because what we are trying to prove is that the integral of g is dominated by the integral of f when both are defined. So we can indeed make this assumption, again, because otherwise the conclusion of the theorem holds trivially. And the opposite case, when the integral of g minus is finite, then is exactly the same argument, just replacing f by minus g, and g by minus f, and following the same approach. Now, we're assuming f is larger than g, and that means the positive part of f dominates the positive part of g, and the negative part of f is dominated by the negative part of g. To see that, we just need to see what is the positive part of something. This is the function. This is the graph of the function y equal positive part of x. It is a non-decreasing function, and this would be the graph of the function a negative part. This is a y. This is y equal negative part of x. So this is a non-increasing function. So if f was comparable with g, we assume f is comparable with g, then the positive parts and negative parts are also comparable in the right direction. And from there, we can conclude, because we have already established the property of monotonicity for non-negative functions, and these are non-negative, and we can do the same here for these are also non-negative functions, the negative parts of f and negative parts of g. We can do that comparison. And here I'm already flipping the comparison because I add a minus sign in front of it. And now we can add these two inequalities together. When we add these two inequalities together, we know we do not have plus infinity, minus infinity on both sides. Why? Well, because from this assumption, these numbers, both these numbers here are finite. So we can just add them to this inequality here. And from here, we can conclude the integral of g stays below the integral of f. We do not get a infinity minus infinity operation exactly because these two are finite. And as I said already, the case when expectation of g minus is finite instead of expectation of f plus, this will apply, the case will be handled identically. We just need to switch f by minus g and g by minus f, and we'll be in the previous case. Now we want to prove that the Lebesgue integral is homogeneous. Homogeneous means if we have a number alpha that can be can take infinite values, it can be any number alpha. Well, let's suppose first alpha is non-positive. Just to consider this case first. If it was the opposite case, if alpha was non-negative, we could replace f by minus f and alpha by minus alpha and get the same conclusion. So we're multiplying f by this number, which is negative or non-positive. So how can we do that? Well, the positive part of this function is minus alpha times f minus. And the negative part of this function is minus alpha times f plus. So we're just applying the definition of integral, assuming this one is defined, then we can split it like this, positive part, negative part with a minus sign in between. And this number here is a non-negative number. We have already proved homogeneity for functions which are non-negative. So this non-negative number, it can go out. It can go out here. Likewise, this non-negative number can go out here. And now we can just combine these two numbers together. And these two numbers together, their difference is here. Their difference is not plus infinity minus infinity, because we are assuming that these integrals are well defined. Or well, if this one is well defined, then at least one of these two will be finite, which means at least one of these two will be finite unless alpha equals to 0. So let's first suppose alpha is not 0, and then one of these two is finite, which means this is well defined. This does not give plus infinity minus infinity, and it equals the integral of f. Okay, this as long as alpha is not 0, we can go from this being well defined to this being well defined. If alpha equals 0, this holds trivially as long as this is well defined. So the property of homogeneity for Lebesgue integral, it assumes both integrals are defined. And we can go back from this. If both are defined and alpha is not 0, we have this identity, and this concludes the proof. So we're now going to prove additivity of the Lebesgue integral for extended Borel functions. We have already proved additivity of the integral for simple random functions, and using approximation by simple functions and monotone convergence theorem, we have already proved also for non-negative extended Borel functions additivity. And now we're going to use that to go from non-negative to the general case. So what is the statement? The statement is, given two extended Borel functions, f and g, suppose the integral of these two functions is defined, and suppose we can add the integral of these two functions. What does it mean to add? It means these two functions are not both infinite with opposite signs, plus infinity, minus infinity, or minus infinity plus infinity does not occur. And also assume that these functions, we can add these functions, which means either they are never plus infinity or minus infinity at the same time, or the set where this occurs has measure 0, and then we can, on that set of measure 0, just redefine f and g to be both have the same value, let's say 0. It will not change the value of any integral, it will just clear any problem in defining this sum here. So we're assuming these two are not both infinite with opposite signs, and for this reason, we can assume that none of these is minus infinity. So this integral is not minus infinity, and this integral is not minus infinity. And why is that? Because, well, if one of these is minus infinity, then we can just substitute f, let's put minus f instead of f, and g, let's put minus g instead of g. And if one of them was minus infinity, when we do that substitution, it is no longer minus infinity. And the other one could not have been plus infinity in that case, because that case has been excluded, that this sum is well defined. So when we switch the signal, then it would not be able to become minus infinity, because it cannot be plus infinity in that case. So in summary, we can assume that none of these two is minus infinity. Now, to say that the integral of f is defined and it's not minus infinity, it also means that the set where f equals minus infinity, the measure of that set is 0. And this set of measure 0, we can redefine the function f, replace it by another function, and just make it some number there different from minus infinity, let's say 0. So we can assume f is never minus infinity, just by considering a different function, f tilde, such that f tilde equals f almost everywhere, and we just remove from the points where it was equal to minus infinity, and consider f tilde instead. So we can assume that f is never minus infinity, and for the same reason, we can assume g is never minus infinity. So in summary, by supposing that these functions f and g can be integrated and that their sum is defined, we have established that without loss of generality, the integral of the negative part of f is finite, the integral of negative part of g is finite, and from there we also show that we can assume without loss of generality that f is never minus infinity and g is never minus infinity. And supposing this, then the trick to prove additivity is to write f plus g expanded in two different ways. One way is take f, split it into positive and negative parts, take g, split it into positive and negative parts, and alternatively, group f and g together and split their sum into a positive and a negative part. Now, once we have established both these inequalities, or both these equalities, we can ignore that we started from this and just use that these two things are equal, these two expressions are equal, and now we can use the assumption that f and g never take value minus infinity, which means this number here is a finite number, this number here is a finite number, and this number here is a finite number. Okay? They can be 0, but they cannot be negative. They cannot be infinite. So we can add g plus, f minus, g minus, f minus, and f plus g minus. We can add it to both sides of this equation, because these are finite numbers. When we do that, then of course, when we edit this, since it has a minus sign, it will disappear, and they will just appear here. And since this is a minus sign, when we add f plus g minus to both sides of the equation, it will appear here, and it will cancel here. So now we are left with this equality to work with. These are all non-negative functions. So we have done this very slick trick to make assumptions that hold without loss of generality to arrive at an identity that is only considers non-negative functions. And now we can use what we have established already, that the integral is additive for non-negative functions. So we can write this integral plus, we can just integrate everything here. This integral plus this integral plus this integral will be equal to this integral plus this integral. But now we have already assumed that the integral of f minus is finite. The integral of g minus is finite, so we can add both f minus and g minus and use this inequality here. F plus g minus is at most f minus plus g minus. This is a useful inequality satisfied by this function negative part. And so here we can, so this integral is also finite. So the point is, this integral will also be finite because this integral is finite, this integral is finite. So we can, since this integral is finite, we can subtract it from both sides. This is just a finite number, we can take it out. So when we subtract it from both sides, it will disappear here and appear here with a minus sign. And likewise, we can subtract this and this from both sides because these are finite numbers. Look how many careful considerations we have to do when we are operating with numbers that can be infinite, but we can do that. We can subtract these numbers from both sides because we're assuming they're all finite. And now we look what we ended up with. This, which is nothing but the integral of f plus g. This, which is nothing but the integral of f. And this, which is nothing but the integral of g. And this concludes the proof of additivity, and this concludes the longest video lecture we've had so far. Have a good weekend.